In this module, we will learn why training forever is not a good idea and that training must stop. Say, for example, you're trying to solve a problem where the problem is given someone's face picture, you want to predict whether that face represents a happy mood, a sad mood, a crying mood, or a laughing mood. And say you are working at a company and your boss asks you to do this. As a solution, what you do is you collect the picture of everyone in your company and train a deep learning model using all the pictures as your input to train the model. And then you train for a really long time. Train long time to obtain very good accuracy, right? So you've used all your data, to train a deep learning model, and you train for a very long time, and the accuracy that you'll obviously get is almost 100%, right? So you'll get very good accuracy. So you go to your boss and you say, hey, I solved the problem. I really did what needed to be done. This is how you're going to feel. Your colleagues will congratulate you for achieving really good results. But inside, you know that you used all the data to train the model. So obviously, if I train using the whole data set, or if I train on the data set on which I'm supposed to make prediction, then I'll have a very good accuracy. But inside, you will know that that is not the right way to go. You did not test your model accurately. So what's the correct approach? Let's look at that. The correct approach is to use callbacks and of course data splitting and all of that, but we will focus in this module on something known as callbacks. Without callbacks, training your model is like throwing a paper plane where once the paper plane is out of your hand, after your initial impulse, you don't have any control over its trajectory or its landing spot. However, with callbacks, training your model is like controlling a drone with a remote in your hand, where you can stop the training whenever you want or do anything that you would like to do with the model based on the controls that you have at your hand. Now, of course, we have to correctly split the data too. And this is what we're going to discuss now. In deep learning, you will hear many people frequently use the term development set, training set, validation set, and test set. It is important that we understand the difference between all four of these sets. The training set is the set which you run your learning algorithm on. That is the set that you use to build your model. Build your model during training. Dev set is the one which you use to tune hyperparameters, select features, and make other decisions regarding the learning of the algorithm. So dev set is a set larger than the training set, which contains the training set itself. Test set is the one which you use to evaluate the performance of the algorithm, but not to make any decisions regarding what the learning algorithm or parameters to use. Overall, if this is your entire data set, then this is how we split. Maybe we keep 20% as the test set, another 20% as the validation set, and the remaining 60% as the training set. So usually people have been hearing that, or we have been hearing that we have training set and we have validation set or test set, and we use this term interchangeably, that is validation and test. But in deep learning, there is a difference between the two. In deep learning, what we do is we randomly shuffle and create our test set, validation set, and training set. And once we have a test set, we never touch it for training or anything like that. Now, on the training set, you design your neural network, right? And then you evaluate on the validation set. If your accuracy on the validation set looks good, then you say, I'm done. But if not, then you go back and keep training, design a new model, and you basically tune your hyperparameters, which is the number of layers, number of neurons in each layer, and all the hyperparameters in neural network. You will tune all of your hyperparameters on the validation set using the validation set, because you don't use the validation set to train the model. And once you get a really good accuracy on the validation set, then you say, I am done. And then you evaluate on the test set, and whatever accuracy you get on the test set becomes the performance of your model. This will be like a blind test of your model. Earlier, what machine learning experts used to do was split the data into training and validation, and then train the model using training set, but then pick the best model which has highest accuracy on the validation set. This is wrong, because I can keep trying all possible hyperparameters to get the highest possible accuracy on the validation set. A much fairer way of evaluating the model is to do this, that is, we allow the developer to do this, but then when testing the model, we should use an independent set. Now, going back to our example, here, what your boss should have done is split the data and kept maybe a portion of the data as test set to himself or herself, and let you develop a deep learning model with the remaining data. And once you are done training, evaluate the model on the test data which the model never saw before, either for training or for validation. Now, obviously, correct dataset splitting is very important. After that, what comes in as an important technique is model checkpointing and early stopping. So model checkpointing is saving weights of the model during training, during every epoch or every few epochs. Here's an example. Say we have a model.fit statement in your training code with certain epochs and batch size certain. All you have to do is add a callback to your model, where you can define your callback with something like this. This is model checkpointing, so it saves a model after every few epochs of training. You specify the file that you want to save your weights to, and you also want to specify what you want to monitor. And you also say save best only as true, so that you don't have overlaps. Now, something that's very interesting about this is you want to know what happens when you change your validation loss to only loss. So instead of validation loss, if we monitor loss, what's going to happen? So with validation loss in place, what the checkpointing does is every time we get a better model on the validation set, it saves it. It saves it into the model.h5 file. Instead, if we change this val loss to simply loss, then instead of saving the best model on the validation set, it's going to save the best model on the training set, which means as long as the model keeps improving on the training set, it'll keep saving new model. Not very helpful, so you probably don't want to do this. Now, once the model is trained, you can actually download the model and save it into your local computer to use it later for making predictions. Early stopping is interrupting the training once a target metric being monitored has stopped improving for a fixed number of epochs. Say this is my learning curve, right? And let's say this is my training loss, and in x-axis I have epochs. It keeps going down, but then the validation loss goes down and then goes back up after some time. Early stopping is saying stop the training if it does not improve after a certain number of epochs, which is controlled by the parameter patience. So I can create another callback B where I specify if my validation accuracy does not improve for 100 epochs, then stop training at all. So once again, I can simply do callbacks A and B, and it'll call both model checkpointing and early stopping. Now, what happens if we choose accuracy instead of validation accuracy here? So once again, if we replace validation accuracy with accuracy, it probably will never stop, because early stopping will kick in only when your accuracy does not improve after 100 epochs. But on the training set, if we look for accuracy, if we early stop based on training accuracy, then early stopping becomes not so useful, because the training accuracy will always usually keep going higher. So this is a bad idea. We always have to use validation accuracy into our early stopping and model checkpointing. Now, another checkpointing technique that's used very commonly and also very helpful is the idea of reduced learning rate on plateau. Now, you may know that when training a model, so say this is my loss function, we are looking for a model that has minimum loss, right? So very low loss. There may be ups and downs, but we are looking for a global minima on the loss. What happens is, by default, your model will jump around from here to here, here to here, and then to here, and then to here, and so on. So it keeps bouncing back and forth in your loss surface with the goal of finding the minimum loss. Now, as we get closer to the bottom of this loss function, it is a good idea to reduce the learning rate. And to do this, all we have to do is include a new callback called reduce learning rate on plateau. We want to observe validation loss. And every time we don't see an improvement for 10 epochs, reduce the learning rate by a factor of 0.1. So do it when validation loss does not improve for 10 epochs. And what to do? Divide the learning rate by 10, so that we are not jumping back and forth in the surface, and in a way we are converging. Now, when you know, when to find out that you need a reduced learning rate on plateau? You will know this by looking at your learning curve. If you see that you in your learning curve, let's say this is my validation learning curve and this is my loss, it goes down, and then if it fluctuates a lot, right, that's when you know that your learning rate is too high. Your learning rate is high. So this is when you want to choose, say if this is 10 epochs and if this is 20 epochs, you may want to do patience equals something like 10 and then factor equals 0.1, such that your learning rate keeps going down, and this should translate into more stabilized learning curve. At the end, I would like to wrap up this module by discussing that you can actually write your own custom callbacks. Keras comes with these 6 methods which you can override or create your own version to do what you want in between training. Say, for example, you have a large data set and you would like to plot the predictions versus true. You would like to do this plot after each epoch to observe the progress. As of now, you have to wait for the entire training to finish before you can do that. But what you can simply do is override the on epoch end method and implement all that you want inside this method, which gets automatically called at the end of every epoch. You can also do whatever you want to do at the beginning of each batch, at the end of each batch, at the end of each epoch, at the beginning of each epoch, or when the training begins and when the training ends.